Okay, thank you very much for the introduction, and I'm really glad to be here at this interesting conference and to have the opportunity to give this talk here. So I will talk about the stability of Einstein metrics, or maybe today a little bit more about instability. And so my goal is to give some kind of survey about recent results. And first I have to explain a bit what it is all about. So I will talk about these Einstein metrics, which are very important in Riemannian geometry, very nice objects. They have this nice property that the Ricci curvature is a multiple of the metric. This multiple here is always E, the Einstein constant, which is scalar curvature over the dimension. It's a real number. And I want to talk about a special class or special properties for these Einstein metrics. And to define this, it's convenient to recall that Einstein metrics are critical points of the so-called Einstein-Hilbert functional. So this functional is defined on the space of metrics, and it maps the metric G to the integral over the scalar curvature. And here I restrict to the space of metrics of volume 1. I could do it without it, then I would have to need to use the normalized volume functional. So this is my functional. And Einstein metrics are critical points, but as is well known, they are saddle points. So they, but there can be maxima, local maxima, if this functional is restricted to some subset of metrics, which are the metrics of, which are denoted by C1, of constant scalar curvature and volume 1. And so now, the question is, what is the behavior of these critical points for this restricted functional? And this behavior can be studied by the second variation, so somehow the Hessian of this function. And we have somehow to see whether this Hessian, the second variation, is positive or what is the behavior. And to do this, we have to consider the following decomposition. So first of all, I will assume in my talk that this manifold is compact and it should be different from the standard sphere. And then it's known that one has three cases to consider. So the tangent space to the space of metrics. So in other words, the symmetric two tensors on this manifold M. This splits into three summands. So the first summand here, this delta, which appears here in the formula, is just the divergence of a symmetric tensor, and the adjoint, the delta star, the adjoint operator, is given by the Lie derivative, the Lie derivative of a vector field X. And then the first summand, which appears here, the image of delta star, is nothing else than the tangent space to the orbit of the action of the diffeomorphism group. And since this function is invariant, it's clear that it is, the second variation is 0 on this space. And then we have the second space, and this is of course the tangent space to the conformal class. And here it's, one can see that the second variation is positive. Here we need the assumption that it's not a sphere. And finally, what is interesting for me here in this talk, so I will restrict to the third summand. So this, as one can see, it's these are symmetric two tensors which are divergence-free and trace-free, and these are called TT tensors, transverse traceless tensors. So they are somehow transversal. These are transversal directions to the orbit of the diffeomorphism group. So I will restrict the second variation just to this subspace and consider it here. And the subspace is also tangent to this set where I want to restrict my functional, this C1. And also here we have a very explicit formula for the second variation. So the second variation of my Einstein-Hilbert functional is given by the L2 scalar product of the things which are written here. So here appears a certain Laplace type operator, the so-called Lichnerowicz Laplace operator. I will tell you more details about this in a moment. And it may be important to say it's elliptic, and so it has discrete spectrum on a compact manifold. And here this 2E is the Einstein constant. And this is the formula on these TT tensors. So now I have everything together to define the stability. And this will be, for redefining this, I will use this Lichnerowicz Laplace operator, and in the end it will be a spectral property of this operator. Okay, so again, I have a compact Einstein manifold with a fixed Einstein constant E, and then I will call a metric, an Einstein metric, stable if the second variation is less than 0. And this is the condition on TT tensors, it's trace-free and divergence-free tensors. And as by the formula which I just showed, this condition is equivalent that the spectrum, which is discrete, the spectrum of this Lichnerowicz Laplace operator is bounded from below by twice the Einstein constant. And this has to be satisfied on TT tensors. And the opposite, so unstable, the metric will be unstable if there's a TT tensor H, a symmetric 2 tensor, such that the second variation is positive. Okay, and then by this definition, this is a definition which goes back to Koiso. So there are certain versions of this definition, but I will use this here. So stable Einstein metrics are just local maxima of this functional if it is restricted to the subspace of metrics of volume 1 and constant scalar curvature. This is clear. And also we have this reformulation for unstable. So unstable means that there's an TT tensor, which is an eigentensor for this Lichnerowicz Laplace operator, for the eigenvalue mu, which should be less than twice the Einstein constant. So if I have such a tensor, such an eigentensor for such an eigenvalue below this critical twice the Einstein constant, then this metric is called unstable. And these T tensors with this property, they are also called destabilizing directions. And it will be a question how to find such destabilizing directions. And then there's a motivation for considering this these stable or unstable Einstein metrics, which comes from the Ricci flow. I will not say much about this, but the Ricci flow can be considered as a dynamical system on the space of metrics, and Einstein metrics are, in a certain sense, a fixed point of this flow. And so we have the stability of this dynamical system, and at least in the one direction we have, if the Einstein metric is unstable in the sense I defined, then it is also dynamically unstable with respect to the Ricci flow. So this is some motivation for also looking for such unstable Einstein metrics. Okay, and here in between stable and unstable, of course, there's a case where this second variation is 0. So these are so-called infinitesimal Einstein deformation. So if I have a curve of Einstein metric, then I can consider the tangent vector to this curve, and this curve, this tangent vector, the symmetric 2 tensor, is then in the kernel of the second variation, and it's called infinitesimal deformation. So I will say a little bit more, but not much on this case here. I'm more interested in stable and unstable. And by these properties of this elliptic operator, it's clear that the space of destabilizing directions and also the space of infinitesimal deformations, they are both finite dimensional spaces. Okay, and now, but how to see whether a metric is stable or unstable? So this is done, also I want to present it in this way, using information on the Lichnerowicz Laplace operator. So I would like now to say a few words about this very nice Laplace type operator. Okay, so the Lichnerowicz Laplace operator, I defined it already. This is here I use it as acting on symmetric 2 tensors. And so it's nabla star nabla plus a certain curvature term. So nabla is just the Levy-Schwider connection. Of course, this extends to connection on symmetric 2 tensors. The nabla star is adjoint. So the first part is already non-negative. And then this Q of R is a certain curvature term. It's a symmetric endomorphism of this bundle of 2 forms. So in any point, it's diagonizable. One has eigenvalues, and it's symmetric and linear. And okay, one can also give an explicit formula, which is maybe not so important here. Usually it's written with this R with a circle above and then Ricci, but here Ricci extended as a derivation on symmetric 2 tensors. And this is formula for this, but it's important to keep in mind that it's a symmetric endomorphism, so it's a zero-order term, and the eigenvalues in certain situations can be calculated and or at least estimated. And then one should say that this Lichtenowitz Laplace operator, by the same formula, you can define it on any, in fact, on any tensor bundle or any associated vector bundle. It's a very for this Q of R, there's a universal formula. And you also can do the same definition, replacing the Levi-Shieler connection by some connection, for instance, connection skew symmetric and parallel torsions, and many formulas remain. Important to remark here is that if you have some parallel bundle, if you have some identification between symmetric two tensors and, for instance, differential forms, which comes from a parallel bundle map, then this map interchanges, for instance, the Lichtenowitz Laplace on symmetric tensors and the Hodge Laplace on forms. So I will use this in a moment. So this is this here, as I write it on symmetric two tensors. This is a special case of a very interesting class of operators. Okay, and as I already said, this is Laplace type, and since the first part, the second order part is non-negative, it's clear that it has only finitely many negative eigenvalues, and moreover, there's a very useful lower bound, and this is the following. If I restrict now to the divergence-free symmetric two tensors, then I have this estimate that the spectrum, you could say the spectrum of the Lichtenowitz Laplace operator is bounded from below by the minimum of the eigenvalue of 2QR of the symmetric endomorphism. This holds on the kernel of the divergence, and interesting is that on the equality just holds for so-called killing tensors. Maybe I can show you the proof of this. Let's see whether it works. So the proof is very easy. So here you have to just write this the difference, and there you can write it as this linear combination of del and this joint operator. So we restrict everything to the kernel of del. Delta is the divergence. Delta is the divergence acting on symmetric two tensors. Just so EI interior nabla EI minus. And then you see that we are restricted, so we only have this, and this is of course non-negative. And the kernel, so the equality just holds in the kernel of del star, but del star, this defines killing tensor. So killing tensor, more general, is a symmetric tensor such that this del bar of it is zero, but you will see that del bar is nothing else than del star, that it's just a complete symmetrization of the covariant derivative of this K tensor here. And also it's known that it's equivalent to the constancy of this function. If you just restrict this function on geodesics, then you get a so-called first integral. So, and moreover, one should always keep in mind that for k equal 1, this is just killing vector field. So that's a very natural generalization of killing vector fields. Okay, so let's go back to the Lichtenowitz Laplace operator. So this was not a complete match. So okay, so we have this estimate, and now we can use this to look for stable metrics. So stable metrics for me is now just metrics such that this Lichtenowitz Laplace operator is bounded below by twice the Einstein constant. So maybe I should mention this twice the Einstein constant. This number appears in several situations. For instance, if I look to this inequality, this lower bound on one forms, then it's a well-known, I think sometimes called Lichtenowitz formula, that the Laplace operator on co-closed one forms is for Einstein metric is larger or equal to twice the Einstein constant. This is one special case of this with equality for killing vector fields. And moreover, this the same inequality is true for the Laplace operator on a killer Einstein manifold on functions. Then it's a bit bounded below by twice the Einstein constant. And also it's interesting to note that these twice the Einstein constant, if I consider a symmetric space with the killing form metric, then twice the Einstein constant is exactly 1, and 1 is the Casimir eigenvalue of the adjoint representation, which will appear later. Okay, so we want to find examples for the moment. I just give you what the examples are. So here I will linearly stable. This means that it includes also this infinitesimal deformations. And first, this was already shown by Koiso using some nice, very simple Weizenberg formula. So if I have a manifold with sectional curvature, with negative sectional curvature, then it's automatically stable. And then this is other result, which maybe is not completely. So this is if I have imaginary killing spinners, then Krönke and Changliang Wang showed that independently showed that this manifold is stable. But here, these manifolds are non-compact. So one needs some version of the stability and this definition, which I will not describe. Then there's another case. If I have a Ricci flat, or if I have a compact manifold with a parallel spinner, then this is automatically Ricci flat. And here, using the very nice formula, very interesting formula of Mackenzie Wang, one can show, or he already showed, that the Lichner-Horowitz Laplace operator is bounded below, also it's non-negative, bounded below by 0, but since then the scalar curvature, the Einstein constant is 0, it follows that manifolds with parallel spinners, in fact, all known examples of Ricci flat manifolds are stable, linear stable. Okay, and then similar result, and this was reproved somehow and extended by Dai, Wang, and Wei, another Wang, and they showed that also for compact Kähler-Einstein manifolds with non-positive scalar curvature, they are stable. So these are examples. And then, of course, there are many compact irreducible symmetric spaces like the sphere or the complex projective space. They are all stable. And I will come to this in a second. And so we should remark here that so until now, so all these examples, they have negative or 0 scalar curvature, or they are symmetric. And there are no other example of a stable Einstein metric of positive scalar curvature, non-symmetric, was known. And only quite recently, so a few months ago, we showed that this nice normal homogeneous space E7 over PSO8 is indeed the normal metric here, is stable and is Einstein and has positive scalar curvature. This is a result which we obtained together with Paul Schwan and Gregor Weingart, and maybe I can say a few words in the end. Okay, this was the first example of stable Einstein metrics of positive scalar curvature, non-symmetric. Okay, so now I would like first to continue a bit and say what is the situation for symmetric spaces. To say this makes this last point a bit more explicit. And here, so we have, so this was all more or less done by Koiso in the 80s. He more or less classified or answered the question which compact irreducible symmetric spaces are stable or unstable. And the situation is the following. First one has these symmetric spaces with infinitesimal Einstein deformations. So this was the case where the second variation is 0. Then maybe I first give the list and then say a few words to it. Then we had these unstable symmetric spaces. You can see that only very few examples are unstable. And finally, so all the rest of the symmetric spaces of compact type irreducible are stable. For instance, the sphere and CPN, as I already mentioned, but also the quaternion projective space and the scaly plane. And in fact, so this the stability status was finally decided in 2 articles, one of Paul Schwan, which is also here at the conference. And so he decided the situation for these spaces S4 SUN and E6 over F4. Here it was for these spaces, it was known that there have this infinitesimal deformation. So there's this eigenvalue twice the Einstein constant for the Lichner-Horowitz Laplace operator is realized, but it was not known whether there are these destabilizing directions. So TT tensors, which are eigentensors for the Laplace, Lichner-Horowitz Laplace for eigenvalues below this critical twice Einstein constant. So he could decide this. And together with Gregor Weingart, we showed that these two spaces here, this quaternionic Grassmannians, and these two, we showed that they are unstable, and we showed that these two spaces, they are stable. So these four spaces somehow were left by Koiso in the work of Koiso. Also, I should say that this space here, this quadratic, was later found by Gasky. No, this is a complete. So you should find more all. So HPN is should be stable. So here I have this. I have R is larger or equal to 2. No. Sorry. Yeah, I wanted to say what our contribution was. So the contribution is this HPN is here in all other symmetric spaces. Sorry, this was not completely clear. So these two spaces, there was not known whether they are stable or not. For HPN, for some strange reason, I do not know why, for n larger than 2, it was known that they are stable, but not for HP2. And so, okay, so this is now for these compact symmetric spaces, irreducible. This is now completely clear what the stability is. But I should mention what is now a very interesting question. So it's here, we have here this, in this line, these symmetric spaces with infinitesimal deformations. But if you have this such an infinitesimal deformation, then the big question is whether there's a real curve of Einstein metrics, such that this is a tangent vector to this curve. This is a rigidity problem, or it's a question of whether it's integrable. And in fact, this was, there was more or less, in the irreducible case, there was no example of a manifold of a symmetric space where this question could be answered. And only quite recently here, for SUN, this space, this was shown, and also only in the case n odd, it was shown by Murphy, Hall, Bartat, and they showed recently that these infinitesimal deformations for SUN and odd are not integrable. So they cannot come from curves of Einstein metric. So this means that the Einstein metric, this bi-invariant Einstein metric on SUN is isolated in this moduli space. And so, but for all other spaces here on the list, it's still an open question. So this, to decide whether these spaces are whether these infinitesimal deformations are integrable to curves. This might be an interesting question. Okay, so this was the situation of stability, or here for symmetric spaces. And so I would like to continue with examples of unstable Einstein metrics. And in fact, there are many examples of Einstein metrics, as I already told. All known examples are that the symmetric spaces are unstable. And as far as I know, there are 4 main sources of such unstable Einstein metrics. So unstable means that I have this subcritical eigenvalue less than twice the Einstein constant. And one very good source is these are these so-called Riemannian submersions. And it turns out that the metric G on the total space is unstable under the condition that the Einstein constant of the fiber, here F, is larger than 1/2 the Einstein constant of the base, is some condition. And then one can explicitly write down the destabilizing direction, which is just the combination of the metric G and the pullback of the metric from the base. And this is just the combination so that you get a trace-free tensor. This, so there are several papers of Changliang Wang and Mackenzie Wang. They investigated this and found many examples of Riemannian submersions satisfying this condition and having in the end unstable Einstein metrics on the total space. And in particular case, a particular application is of course, the trivial case of a Riemannian submersion is the Riemannian as a product of Einstein metrics, and this is unstable. And also if the base metric is Einstein and the total metric is Einstein, then there's this condition here exactly implies that there's not only G, but there's a second Einstein metric in the so-called canonical variation. So the canonical variation is that one scales the metric on the fiber. And so for say parameter 1, one obtains this metric G. But under this condition, there's a second Einstein metric. And the second Einstein metric is automatically and very easily to see it's unstable. And so, for instance, there's a huge class of so-called 3 Sasaki manifolds, which fiber over quaternion Kähler orbifolds. And there's a second Einstein metric. So 3 Sasaki metric is automatically Einstein, but there is a second Einstein metric, and this is always unstable. And maybe the most well-known example is the so-called squashed or Jensen sphere, which is, or Berger sphere, which is the second Einstein metric for the sphere of dimension 4n plus 3, and this is unstable. Okay, so this, there are many more examples using Riemann submersions. Then there's another class where I cannot say much about this, but there's a very fundamental and important paper by Böhm, Wang, and Ziller. And also using these methods there a little bit later from Christoph Böhm, he proved the existence of unstable Einstein metrics using certain variational principles after this paper there. And then I want to say a bit more about another class of examples. And it turns out that these unstable Einstein metrics or these destabilizing directions, they are somehow related to harmonic forms. And the first result in this direction, this was from Strauch, Hamilton, and Ilmanen. So they showed here that if I have a Kähler-Einstein manifold with positive scalar curvature and second Betti number larger or equal to 2, then this Kähler-Einstein metric is unstable. And the proof, in fact, is more or less easy, since if the second Betti number is, of course, first it's known that the harmonic forms, harmonic 2 forms are just in H11. And so if the second Betti number is larger or equal to 2, then there's a harmonic form which is orthogonal to the Kähler form. So it's a harmonic form, it's in the kernel of the Laplace operator. And as I said in the beginning, so these 1-1 forms, so 2 forms of type 1-1, the space can be identified with symmetric tensors, symmetric 2 tensors commuting with the complex structure. And this identification is a parallel bundle map, and this interchanges the Laplace, Hodge Laplace operator on 2 forms with the Lichtenrovich Laplace operator on symmetric tensors. And this means that if I take such a harmonic form and compose it with J, then I get an eigenform of the Lichtenrovich eigenvalue for the eigenvalue 0. And then it's, since the Einstein constant is positive, then this metric has to be unstable. Okay, this is about harmonic forms. And then recently, Jorge Lauret started a program to consider so-called G-stable or G-unstable metrics. So his idea was to consider homogeneous spaces and to restrict this Einstein-Hilbert functional to G-invariant metrics, and to discuss the stability for this restricted functional. And the good point is that he found many examples of, for instance, G-unstable metrics, unstable in the sense, so these are invariant metrics, and this reduces to a linear problem, which is not easy, but it's solvable. And but the good point is that all these unstable metrics, G-unstable metrics, they are automatically unstable in this larger sense, which I introduced here. And of course, it's not true in the other direction. So they produced, there are several articles now, also with Emilio Lauret and Cynthia Will. They looked to lists of homogeneous spaces and decided this G stability question. And they found also several examples of G stable metrics. So that this functional restricted to this the second variation that is positive. Okay, and then these G stable metrics are now candidates for stable metrics. And so this was also how we found this, or how we came to this maybe a little bit strange homogeneous space E7 over PSO8. This appeared in one of these lists by Laurette, and this was a G-stable metric, and we could show that it is in fact also stable in a much larger sense, allowing variations through our possible kinds of metrics. Okay, so now maybe I come to another topic. So I would like to say, to explain you a bit how these destabilizing directions, or this is related to killing spinors now. And so maybe I can recall what is a killing spinor. So for this, I have a spin manifold and I have the spin bundle, and a section of the spin bundle is called killing spinor. If it satisfies this equation, that's a covariant derivative, it's a multiple of X Clifford multiplication with the spinor. This is a very nice class of objects. So for instance, if I have such a killing spinor, then the metric is automatically Einstein and has positive scalar curvature. So here I restrict to the case where this constant lambda is a real number. Of course, this could be also purely imaginary number. This would be the case of imaginary killing spinors, which I mentioned in the beginning. These are, as shown by Changliang Wang and Krönke, these are stable, but these are non-compact manifolds. Now I restrict to the case where this lambda is a real number, and then the scalar curvature is positive and the metric is Einstein. And also restrict to the case that lambda is different from 0. Of course, if lambda would be 0, then I just have a parallel spinor, and the existence of parallel spinors implies that it is stable. But it turns out that all known examples of as far as one knows, that all existing examples of these manifolds with killing spinors, where one can compute this, are unstable, and this I would like to describe. But first, these killing spinors, in fact, the sphere is also a manifold with killing spinors, which is I have to exclude. But other than the sphere, these manifolds with killing spinors are all non-symmetric, and in fact they belong to these 4 classes. They can be either Einstein-Sasaki, free-Sasaki, which is a special case of Einstein-Sasaki. And also we have this class of nearly Kähler manifolds in dimension 6 and so-called nearly parallel G2 manifolds in dimension 7. So these are 4 classes of manifolds, and they all admit these killing spinors. And maybe I also should say that the nice property of having these killing spinors is that the metric cone over these manifolds has a parallel spinor, and by this has reduced holonomy. And also, there in all these cases, there's a canonical connection with skew symmetric and parallel torsion. Okay, so this is the situation, and it turns out that for all these classes, one has some instability result, and this we did together with Mackenzie Wang and Changliang Wang in 2 articles. So this is our result, just a list, and here the first 3 cases. You see that again the situation of the existence of harmonic forms. Here, for instance, second Betti number for Einstein-Sasaki, or second or third Betti number for nearly Kähler manifolds. This existence of harmonic forms implies instability, and also we have this last case here, the so-called Berger space, which is a bit special, since this is a homology sphere, so there are no harmonic forms, but nevertheless, it turns out to be, this has an Einstein metric, and this Einstein metric turns out to be unstable. So maybe a few remarks. Okay, as I said, 3 Sasaki manifolds are particular Einstein Sasaki. Here, Simon Salomon and Chris Galitsky, they showed that all odd Betti numbers are 0. Just to recall, I also said, okay, here we have this class of nearly G2 manifolds in dimension 7, and there are three classes according to the number of killing spinors. They are either Einstein-Sasaki, 3 Sasaki, or what we call proper G2. This can also be characterized by the holonomy of the cone. And here the problem is a little bit that that there are no examples. Okay, I should say here there are two questions. The first question, whether there are proper nearly G2 manifolds with third Betti number positive. So we show here that if the third Betti number is positive, then it's unstable. But the problem is that all known examples, so either the Berger space or Alavalla spaces, or the second Einstein metric on Shisasaki metrics, for which one has this P3, it's a 0. Okay, so, okay, and also, for instance, in the case of G2 manifolds, there's only one Betti number left, it's the second Betti number. So, yeah, maybe if the second Betti number is positive, maybe it's unstable, but this we couldn't show since there's, yeah, what is the idea to show these things? It's again that one wants to come from a harmonic form to a symmetric tensor, which is an eigentensor of the Laplace operator, the Lichner-Horowitz Laplace operator for subcritical eigenvalue. Of course, here for these manifolds, we do not have this nice holonomy restriction, but we have this canonical connection. And so we can use this canonical connection and do the same thing that I mentioned for Kähler-Einstein for the canonical connection and the Laplace operator for this canonical connection. And then, but then one needs formulas to compare the Laplace operator for this canonical connection and for the Levi-Shiller connection. These formulas we developed a few years ago with André Moriano, so we could use this and produce the subcritical eigenvalues. Okay, but this idea we couldn't use for the Berger space, and maybe I could can explain a little bit. As, yeah, it's more or less the end here. I could perhaps explain a bit how to prove the existence. So here this, how to prove that the Berger space is unstable. Okay, maybe this one proof to give a few details so you can see how it works. Okay, what does not work? Okay, let's see again. Yeah. So Berger space. So Berger space is a very nice space. This was also used by Brian to find the first non-complete example of holonomy spin 7 as a cone over the space. No, sorry, sorry, but okay. So this I will write it here, not with SO. So what is the definition? For instance, here I use the SO5, and then I embed this group SO3, but not the standard embedding, but using the 5-dimensional irreducible representation. And this is the embedding I have to use. And the same, but I will use SP2 since it's easier to write down the representation theory. And then the Lie algebra of SP2 splits in SP1, the Lie algebra of the small group, and the complement, which is then identified as the attention space. And it turns out that this complement is just the sixth symmetric power of E, where E is the standard representation. So in particular, it's an irreducible representation. So this space is an isotropy irreducible homogeneous space. So the one has this Einstein metric given by the killing form. And now the main idea, which we also use somehow for the results on symmetric spaces, is that, so I want to consider the sections of this bundle of symmetric 2 tensors, and I restrict to trace-free. This is a 0 here. So I have this space of trace-free symmetric 2 tensors over this homogeneous space G over K. And this is, of course, a representation of the group G. It's by the left regular representation. And it's this Peter Weil or Frobenius reciprocity to decompose the left-hand side, this G representation in irreducible components. And here you see on the right side, the components here are certain SP2 representations. They are parameterized by 2 integers, K and L. And whether this representation appears or not is decided by this home space here. So the idea is that one has this VKL, this is an SP2 representation, so one has to restrict it to SP1. And the same, also the sim2 of MC is not irreducible, so we have to decompose it, and then to see whether there are common components. And if there are common components, then this representation appears here. And then it's easy to calculate eigenvalues of Laplace type operators, at least in principle, since if I consider the Laplace operator for the normal connection, for the canonical reductive connection, then it's just a Casimir operator here on the space, and Casimir they can be calculated. But okay, I will not use this, but the following argument here. I just consider the following representation. This is V11. It's a 5-dimensional representation, 5-dimensional SP2 representation. But it turns out if I restrict this representation to SP1, then it's still irreducible. And as an SP1 representation, it's sim for symmetric power of E. And okay, and now I have to see, first claim is that this representation indeed appears in the sum over here. And this, as I said, first you have to decompose the second symmetric power of this isotropy representation. And you see, okay, there is sim for E appears. Okay, and this means that this representation V11 contributes to symmetric 2 tensors. This is the first remark. And then the second remark, by using the same argument, now that this common summands do not appear, you can show that this representation does not contribute to tangent vectors and not to symmetric 3 tensors. But this has the conclusion that this representation belongs to the kernel of the divergence and its adjoint operator. And since this, these two operators, the divergence and its adjoint operator, they are invariant operators. So one can restrict to representations. And since I know that they do not appear in tangent here, the divergence would lead to tangent vectors. The adjoint would lead to symmetric 3 tensors, but this representation does not appear here, so this has to be 0. But this intersection, maybe you remember from the beginning of the talk, these are just killing tensors and of course also TT tensors. But then I had this lower bound for the Lichnerowicz Laplace operator, and exactly on killing tensors and in the kernel of delta, we had this equality. So the Lichnerowicz Laplace operator is just twice this curvature operator, exactly on this representation V11. And then now it remains to calculate what are the eigenvalues of this QR, or what is this QR, and this can be done since we had a comparison formula between this curvature expression for the Riemannian curvature and for this canonical connection curvature. And yeah, it turns out that it's exactly 19/3, and then this normalization which we used here, this it's just less than twice the Einstein constant. And so this means altogether, okay, here we use this two things, I should say. First, we use that this curvature expression for this canonical connection is just the Casimir of the small group. And also we use the comparison formula for this difference. This was done in an article with Bogdan Alexandrov and one with Andrei Morianu. And then it turns out that indeed this one space, this V11, this gives destabilizing directions. And moreover, these are killing tensors. Okay, sorry. Okay, this is all what I want to say here. And yeah, maybe I just return. And thank you very much for your attention.